Hello everyone, this is Dr. Vaughn. In today's video we're going to be talking about an example of Bayes' theorem. Now Bayes' theorem is one of the topics in this week's unit. I'm going to be doing an example here that I've created. It has actually three different branches to it: factory A, factory B, and factory C, which is a little bit different than most of the examples that are in your book, which only have two cases. They talk about A and the complement of A, or A and not A. So they're only chopping up your sample space or your population into two pieces. We're going to make this a little bit more complicated and look at an example where we chop it up into three pieces. But the basic idea is the same, and I want to show you some of the power of thinking about Bayes' theorem. So the stem of the problem is given right up in the top. We're given the factory defect rate. So this is they're producing objects. We're going to call those objects widgets. And this is how many of those widgets come off of the production line as being defective. So 4% at factory A, 5% at factory B, 7% at factory C. We're also given how much of the total production overall comes from each of these three factories: 40%, 30%, and 30%. So you notice that these add up to 100. So all of the widgets that are produced for this particular example come from one of these three factories. Now I like to think about Bayes' formula and these conditional probabilities in terms of tree diagrams. So I've tried to set this up with a little text-based tree diagram here. This is how the probabilities are kind of laid out for us. We have, the total production of all the widgets that come from either factory A, factory B, or factory C. So we could label the branches of this tree diagram with the corresponding percentages. The probability of landing up at this node, if you pick a widget at random, the probability that it's produced at factor A would be 40%. And this would be 0.3 for 30% and 0.3 for 30%. Now these second level of branches represent the conditional probabilities. So given the fact that I know that I'm at factory A, then I know what the defective rate is, and that's this 4%. So conditioned on the fact that you're at factory A, the probability that you produce a defective widget is 0.04 or 4%, and therefore the probability of it becoming not defective would be 96% or 0.96. So you could fill out all of the branches of this tree diagram and assign them the corresponding probabilities just from the numbers that are given up in the stem of the problem. Now let's look at the question that's being asked. If a widget is selected at random is defective, what's the probability that it came from factory A? So what I want you to notice here is that the conditioning in the question is backwards from the conditioning that's actually given to you in the problem. So if I know that I'm at factory A, then I know what the probability of something being defective is. But the question is saying, if I know that it's defective, now what's the probability that it came from factory A? The conditioning is opposite from the conditioning that's given to you in the problem. And that's a classic tip-off that you're dealing with a Bayes theorem problem. So think about that as you're kind of looking through the problems in your book. So the next thing that I want to do is actually translate this into the language of probability using sets and events and probability notation. So we'll define event A. Remember, an event is just a subset of the sample space, as being the widgets that come from factory A. So the probability of being in set A, or the probability of a widget coming from factory A, is just 40%. If you picked one at random and 40% of them are produced at factory A, then you have a 40% or 0.4 chance of actually selecting a widget that was produced there, and so forth. So these are just the kind of the same data that was given up over here in the problem, but written as probability statements and using set notation. Then down here what we have is the conditional probability statements. So what's the probability of D conditioned on or given the fact that A is true? So that's how you read this: the probability of D given A. What's the probability that it's defective given that I know that I'm in set A, or that it came from factory A? And that's the defect rate for factory A. So what's the probability that it's defective if I know that it came from factory A? That's 4%. So we write that as a decimal as 0.04. And similarly the 0.05 and the 0.07. So these are the conditional probabilities we know: the probability of it being defective if it came from a certain factory. These are the probabilities of it coming from a certain factory. And what we want now is the opposite. We have here the probability of D. Oh, there's a typo here. This should be the probability of D given C. What we have here is the probability of D given A, and what we want is the probability of A given D. What's the probability that it came from factory A given the fact that I know that it's defective, which is how we define set event D to be. All right, so Bayes' theorem shows you how to turn this conditioning around. The probability of A given D is given by the probability of D given A, the opposite conditioning, times the probability of A, divided by the sum of those same products over each of the three different possible sets that it came from. What I want you to make note of in Bayes' theorem right here is that the numerator is the product of the branches where you go from here to factory A to being defective. So this number, 0.4, times this number, 0.04, is exactly the product that is expressed in the numerator of this fraction. And the denominator of the fraction, the first term, is actually the same as the numerator, and the second and third term are those same products on these other two branches of the tree diagram. The probability of B times the probability of D given B, and the probability of C times the probability of D given C. So the Bayes' theorem is really the one branch of the tree that's showing up where you're defective and at factory A, divided by the sum of all of the different branches of the tree that end at the widget being defective. So that's our Bayes formula, and now all we have to do is really do the computation. Okay, we have all of the numbers that are expressed in this formula. We wrote them all out right here. So at this point, all we have to do is plug in the numbers and do a computation. So I'll just flip back and forth. I'm going to go into my equation editor. I'll type that the probability that we're looking of A given D is equal to, we'll set up a fraction bar, and in the numerator we have the probability of D given A, which is 0.04, times the probability of A, which is 0.4. So that's going to be 0.04 times 0.04 times 0.4. And in the denominator, you have the same thing, 0.04 times 0.4. But then we have to add the other two branches. So now we have the defect rate of 0.05 for factory B times the probability that it came from B, which is 30%, so 0.3. And then we have to add in the last defect rate, which was 7%, and then 30% of the widgets came from that factory right there. Okay, so at this point we just have to do a little computation. I'm going to do this on my calculator. The numerator, 0.04 times 0.4, gives me a 0.016. And in the denominator, we have the sum of 0.016 plus next product, 0.05 times 0.3. That should be 0.015. Plus, and then the last term should be 0.021. 0.07 times 0.3. We add those up in the denominator. So we have the numerator, 0.016, divided by, now the denominator is 0.052. And when you divide, you end up with 0.3077 or about 30.77%. All right, that's our example of Bayes' theorem. I hope this has been useful to you, and best wishes this week.